In this video, we'll be looking at the other two transformations covered in geometry, rotations and dilations. A rotation is a transformation in which a figure is turned about a fixed point called the center of rotation. Simply put, a rotation turns a figure. But when we really start thinking about this on the coordinate grid, or if we're doing something, say, scientific like physics, we need to be able to identify the point that the rotation spins around. Okay, sometimes that point is located in the figure, and then sometimes it's located on the outside. So what I'm going to do real quick is just a quick demonstration of what I'm talking about there. If I had this figure and I want to rotate it, the center rotation could be located in the middle of it, and then the figure just spins around that point. Okay, in other cases, you can have the point that's on the outside of it and then spinning around it. That one's a little bit hard to demonstrate. I'm going to try something first here. I'm going to just say maybe the center is at one of the vertices and it spins like this. I want you to at least be able to visualize that type of a rotation. Okay, I'm going to do that one again. Just, we have it locked in at one of the corners and then we're spinning around it. Okay, and then you can have the point completely outside of it as well, right? I could maybe put a point here. When it rotates, it's going to maintain a distance around that point as it spins like that. All right, the picture that we have here of rotation is the case where the point would be on the outside of it. And this might be a little bit more important that we focus on looking at that one, because when you have the points on the inside or on the edge of it, the way that we're going to approach it, those might actually turn out to be a little bit more confusing. So if you see them separated here, then that's a bit better. Let me go ahead and answer this question, because in the last video, I know that I forgot to answer it both times when we were looking at translations and reflections, and then I came back to it later and answered it. Okay, so does it appear that a rotation is an isometry? The answer is yes, it does. All right, when the figure moves around, just like when I took that piece of paper and I moved it around, as it rotated, it's still the same shape. It was still a rectangle, and it was still the same size. It didn't shrink or didn't grow. Nothing like that happened to it. So yeah, it is an isometry. All right, like with the other transformations, a good approach at working with rotations is to think about them as just individual points and not so much the whole figure. That is if you actually need to create a rotation of it. So the triangles that we have here, they got 3 points, A, B, C, right? Here's your A, B, C, and then these are going to be the new versions of it. You've got A prime, B prime, and C prime. So this figure is actually rotating this direction. It's rotating in a clockwise direction, so it's moving that way. Okay, and a way that we could construct this if we needed to, we could think of the individual points first. So let's just talk about A. Imagine everything else is gone except you've got point A, and then you've got the center rotation, which we're calling P here. If you have that, you can create a line that would connect A to P. Let me go ahead and just add that to the figure. Okay, I can go ahead and connect a line that would be to A to P. So if you're really drawing this, you might do this sort of in a lighter color that you can erase when you're all done with it. But I can connect A to P, and then you're going to have some way of measuring what your rotation would be, and that's going to be in degrees. There's going to be some sort of degree amount that this is going to rotate to get to A prime. Now, since I've already got the picture drawn here, I don't need to actually bother with any measurements. You can see I got it on my protractor now. Well, I'll go ahead and just take a measurement of it so that you can see what the actual values be. Okay, so you got A, which is connected to P, and then P is connected to A prime. So again, sort of, well, I'm going to take a measurement and then I'll pretend that A prime wasn't actually there. So I'm going to take my protractor. You have that center point. The line might not be long enough, but I'll just sort of eyeball it for the sake of the video. Okay, so you're going to put the center, really we have an angle here. We got an angle. I'm going to put the center of the angle at the middle of the protractor, and then I'm going to line up one of the edges here with the 0 marking, and then the other one is looking like it goes at about 120 degrees. You can see a 120, and then you also see 60, but the 0 is on the outside, so we're counting up to about 120. It might be a little bit beyond there. Okay, so maybe like 122 degrees. Okay, so you'd be told some angle measurement that this rotates, and if it's 122 degrees, you would draw a line from A to P, then measure out 122 degrees, and point A prime will be on that line. You would then also make sure that A prime is the same distance away from P that P was from A, and that's how you plot that one. You would then repeat the process with, in example number 1, we're going to go ahead and do a rotation by hand. That means that you are going to be using a protractor to do this. Coincidentally, the angle measurement that I used here, 120 degrees, is pretty close to the angle measurement, the rotational measurement that we have in the picture that was above, except that when I rotate here, I'm actually going to be rotating in a counterclockwise direction. I'm going to be going this way here. So in the last picture, I had measured it in a clockwise direction. The truth is that when we give you an angle measurement and ask you to rotate things, the standard is that it's going to be going counterclockwise. The best way that you can remember that is eventually we're going to be taking this and putting it on a coordinate system. And if you think about the quadrants, you have quadrant 1, 2, 3, 4. Those quadrants are moving in a counterclockwise direction. So our rotation is also going to be that way as well. So same-ish angle measurement, except we're going to be doing this in a different direction. All right, so to start things off, I went ahead and drew the shape that we're going to be rotating, which is just a segment here. That's a good thing because you only need to worry about rotating 2 points instead of doing 3 or more, depending on the number of sides your shape would have. So we only got 2 of them that we got to rotate. And here is a point that we're going to be rotating these about, which is point P. So I went ahead and just drew them to go ahead and have them ready to go. And we're going to do this 1 point at a time. I'm going to use a different color here just because it will get a little bit messy if we're doing everything in one color. So you might want to try that out. All right. What would also be nice is maybe using some dashed lines here, but I'm going to go with solid ones just for, since I'm using a different color, it'll be all right. Okay, so what I'm going to begin with is just a segment that's connecting J to the point of rotation, the center rotation, which is called P. Okay, and now I want to move counterclockwise, which means J is going to be moving in this direction over here. So somewhere there's going to be a line that I need to extend out of P that J prime is going to be sitting on. That line needs to be 120 degrees away from this one. So I'm going to take my protractor and line it up again. Again, put point P right in the center. I have this edge lined up with JP. And for the way I have my protractor set here, when I look at the side, you've got the 180, you got the 0. The 0 is on the inside, so that means I want to be using the inside numbers as I find the 120. So it's going to be the 120 that's over here and not this one. That one would actually be at 60 degrees. So I'm measuring all the way out to 120 degrees. Same thing as 60. I'll put a little dot there just as a marker, and then what I'm going to do is go ahead and connect P to that dot. Now, I only need to go as far out as that line is. Okay, I only need to go as far out as that one. So there's a couple things I can do. I can either just draw a line all the way out to it and then remove what I don't need from it, or I could just go ahead and take a measurement, which inches is a little bit more difficult to work with because you don't have as much detail. So switch over here and look at that. That looks like it's right at 3 centimeters. Not planned, it just is. So right at about 3 centimeters. Now I'm going to line it up with that point that would take us 120 degrees out. And go ahead and draw a segment out to 3 centimeters. Technically, you could just put a dot there and that'd be fine. Wouldn't cause any issues, but I want you to be able to see the whole thing. So that's going to be where J prime's at. We're going to do the same thing to figure out K prime. Okay. So I'll go ahead and connect those, and while I'm here, I'll just take the measurement. Hopefully I'll remember it. That one looks like it's about 3.4 centimeters. So try to remember that. All right, now it starts to get a little bit confusing because we've got a lot of lines on here, but I want to set the protractor again at P, but it's lined up now with K. Once I have that lined up, I can go out to the same 120, which was there. And then, where are we at? My problem was I was about to measure 3.5 centimeters from K. What I want to do is measure 3.5 centimeters from P, or 3.4 is what I had said it was. So at about 3.4, that is going to be the location of K prime. So my J prime's in the way. Go ahead and just move you down a little bit. J prime, and then let's go back to the green color so not everything here is looking red. And I will go ahead and connect these two. All right, and that is the rotation of 120 degrees. If you want to animate it a little bit, here we go, 120 degrees. So we can see that that's rotating out. There's the figure turning out 120 degrees. In geometry, when we move the rotations to the coordinate grid, that's going to be a lot easier than what we are looking at with the rotation just in open space here. Because when we do it on the coordinate grid, we're only going to be looking for 3 particular rotations, which is going to be 90 degrees, 180 degrees, and 270 degrees. Okay, so all of these are going to start with, if you have a point, that would be AB. Okay, so A and B, right now we assume that they're both positive numbers. Now that's not necessarily true. They don't have to be positive numbers. They can be any points, but we're gonna just look at them as if they were positive numbers and sitting in quadrant 1 to start with here. So here's A and B. When you rotate, you're always gonna be rotating counterclockwise unless otherwise told, okay? So when we rotate the coordinate 90 degrees, it's going to take you from quadrant 1 into quadrant 2. If you rotate 180 degrees, you're just basically doing 90 twice, which is going to take you all the way to quadrant 3. And if you rotate 270, that's the same thing as 93 times. So that's going to take you all the way to quadrant 4. And then if you did another 90, it would just be 360, and you'd be right back at the spot you were in. All right, when it does rotate, here's all the answers. They're already in the diagrams for us, so we'll just copy them over. AB, when it rotates 90 degrees, let's take a look at what happens with the coordinates. It becomes negative B and A. So the negative, you can kind of imagine that because we're in quadrant 2. You have to go to the left, which is a negative direction, and then up, which is a positive, so negative and positive. So you see that. But in addition to that, you're going to notice that the letters are flip-flopped. Okay, that now B is in the front and then A is next. So the way that you can think about this, because you might not be in quadrant 1 when you're rotating, you could be in any other quadrant, is to think that a 90-degree rotation is going to switch the X's and the Y's. Then after you switch them, whatever number is now in the X position will be negated. It will become the negative or the opposite of whatever it was. Think about this. If we started in quadrant 2 and we rotated 90 degrees to get to quadrant 3, so we start here and we rotate there, that same argument can be used. It could say we need to flip-flop these, which will give you A, negative B, but whichever one of those ended up in the first spot is now going to be negative. So they flip and you get A, negative B, but then you also change the A to a negative, which is what we get here. Right? They flipped, A moved to the front and became negative, the negative B moved to the back and then stayed as it was. And then you can do the same thing here if you want. You can even look at the very end. These will flip around and the A, which is negative, will become a positive in there. So you can always be building off the 90. If you remember that one, you can always build whatever other ones you need. Of course, 180 is going to end up being the most popular one, and I would really suggest that you memorize that 180 is just the opposites of these. It's actually a really easy one to think of or try and remember, but with everything else, They all kind of get messy trying to remember them, but it is. It's just the opposite of the letters that we got there. So let's go ahead and fill these in. Okay, now before we move on past this and just accept that as truth, I want to do at least a quick demonstration of rotating 90 degrees. The diagram here is pretty good for organizing things, but I don't think it does enough to make you buy into that this is the true mapping for 90 degrees. Okay, so we're gonna just do a quick rotation of 90 here. Oh, and I didn't read it earlier, but this does have the rotation about the origin. It is about the origin, and if that's true, then this applies. If you're gonna rotate around another point, you can actually pretend that the other point is the origin just for the sake of graphing it, and then figure out what the actual coordinates would be afterwards. Sometimes there's neat ways of pretending your object is located somewhere different. You can still get your answers based off of that. Anyhow, in the other video, I think I used this coordinate here. I used 4, 1. It's really good to choose a point that isn't located more in the center area here, but closer to one of the axes, because it's easier to follow what it does when you have a good difference in the numbers that we see here. Like a 4 looks different than a 1. Not just how you write it, but how it looks on the grid. Like 4 is 4 units out, 1 is only 1 unit, like away from the line. All right, so let's suppose this was our A and B. We rotate it around the origin. So if I rotate 90 degrees, all that's gonna do is move this quadrant to here and all the other quadrants around. So that is a 90-degree rotation. Done. All right, now that I have it rotated like that, I can think about where the coordinate landed. Okay, the coordinate, so ignore that for a moment. This is gonna be -1, 4. It's gonna be -1, 4. Okay, so let me go back to where it was. I'll go ahead and plot that one. It was -1 and 4. And if we take a look at the coordinates that we got here, we had 4 and 1. They're gonna flip-flop, so it'll be 1, 4, but the number that moved to the front has also become the negative. So you got -1, 4, and that goes along with what we see here. In example number 2, we're gonna go ahead and practice using the mappings. In particular, what we're going to be doing is a rotation of 270 degrees about the origin. Now let's ballpark some things first. This figure is not sitting like in a quadrant. It's actually sitting on top of the x-axis here. But we're going to be rotating 270 degrees, again counterclockwise. So that's going to be 3/4 turns. Okay, 1/4 turn is going to get it here. 2/4 turns is going to get it here. 3/4 turns is going to get it here. So we know that the figure is going to end up on top of the bottom side of the y-axis. So start plotting points, keep that in mind. All right, now one by one here, let's look for R prime. I'll go ahead and just get all of these ready just in case. T prime and U prime. Okay, mappings. Just, don't make this harder than it needs to, just use the mappings. So up here we got the 270-degree mapping, which says that the points are going to become B and A negative. Negative A, I don't know, I said it backwards there. We got AB, which is going to become B negative A. Okay, so remember, I had mentioned this beforehand here, the points don't have to be in quadrant 1. They don't have to both be positives. The mapping just tells you what to do with them. Okay, so R is both positive numbers, 3 and 1. It's in quadrant 1. So they're going to flip. The second value, the one that came from the front to the back, is going to end up becoming the negative. So you're going to get 1 and -3. For S, they're going to flip as well. You're going to get 1 and -5. And once you sort of get a rhythm of this, you might as well just do all of them, I think, and then just start plotting them. No reason to stop right now. All right, so the other 2 points, they have negatives are in there. Okay, and these symbols here don't mean that things are negative. They mean that you're going to negate them. You're going to make them their opposites. Okay, so let's see. That one's actually not even going to change, is it? All right, because the -3, which is your B, is going to move to the front. So that doesn't even change. And then the 5 will become a negative in the back. So that one doesn't really do any change there. I guess the same thing for the U. They're going to flip-flop. You're going to have -1, and then that one becomes negative. Now, if you did have negative a value, what I was trying to explain there and it didn't happen in the problem, if you had a negative a value to start with, that means that it becomes positive over there. That just means you change its sign. So you can start with two negatives, you can start with two positives, you can start with a mix. These just indicate if they're going to change their signs. All right, so we'll go ahead and start plotting these, and then at some point we'll connect it. We'll see how many we need. We got 1, -3, so we go out 1 and down 3. That's going to be point. I'm not going to label it as R, just going to be looking for the shape. We got 1, -5, so we go 1 and then down 5. Okay, so that line is this line. And T prime is -3, -5, so back 3 and then down 5. And I might as well just plot the last one. It's easy enough. So -1, -2. We get that point. We'll go ahead and connect everything. Yeah, so sometimes you don't really need to plot all of them. Then if you've already got them ready, it's not too bad of a deal just to go ahead and do that. All right, and there's your figure. And it sort of looks like it's just a quarter turn that way, because that would be true, but it is 270 degrees around to that spot. There you are. Let's go ahead and just add that to it. I feel like it needs a little bit more. 270 degrees. A figure has rotational symmetry if it can be mapped onto itself by a rotation of 180 degrees or less about the center of the figure. Okay, so putting it together, there's a point somewhere in the middle. Generally speaking, it is the center of the figure. Now, how do we really decide that? Sometimes it gets a little confusing, but there's a center spot that could be in a figure. They're not all going to have them. They could be in the figure, and if you can rotate around it so that it makes its shape again, then that would be rotational symmetry. Except we're not talking about like a 360 degree rotation, because if we do that, you could literally rotate any figure in the world and end up in spots. So it needs to be limited to like 180 degrees or less. 180 degrees means that you'd have to make at least half of a turn. But if you can make half of a turn and then it ends up on itself, that'd be rotational symmetry. Okay, take a look at the rhombus here. The point, I think most of these, when they do have them, they're pretty easy to know where they are. So there's what we'd call the center there. Okay, that'd be the center of the figure. And if you were to rotate that at 180 degrees, just a halfway turn, rotate at 180 degrees, you wouldn't be able to tell that the figure had been rotated at all. That means that it has rotational symmetry. If you've got to rotate 360 degrees, it does not. We have, this is technically called an octagon because it has 8 sides. It is concave in different areas there, but this also has rotational symmetry. You could have a point right there, and you could actually rotate that one a quarter turn and a half turn, and you wouldn't be able to tell that you've rotated it. Okay, so that one has rotational symmetry, and there's 2 different ways that you could rotate it, quarter turns, or you can do a half turn. Right triangle, it doesn't. Okay, if you rotate it 360 degrees, it's going to look exactly like it was, but you can't rotate it halfway and have it look exactly the same. So halfway would put the long leg on the top, the short leg would be over here. Hypotenuse would pretty much be in the same direction, but it wouldn't be the exact same shape. You'd be able to tell that it had been rotated. Now here's a fun fact. If you're stuck on trying to figure out if a figure has a rotational symmetry, right? If you really can't figure it out and you want to say it's like the right triangle and it's not going to have one, a way that you can identify if it does have one is to think about lines of symmetry. If the figure has at least 2 lines of symmetry, then the point at which they make contact is going to be your center rotation. Let's take a look at the rhombus here. You actually have a line of symmetry right there, because it could, fold across that line and match, reflect through it, and still be the same image. But you also have a second one, which is here. And since you have at least 2 of them, then you will have rotational symmetry, and it's going to be located where they meet up. The octagon, pretty much the same thing, right? You've got here, so there's that spot. But look, any other line of symmetry, you could go diagonally for those. They're all going to meet up, and that's going to be your rotational symmetry, or your point of rotation. The last transformation that we're going to talk about is a dilation. A dilation is a transformation in which a figure changes size by a scale factor. Generally speaking, a scale factor is a number that you multiply by. Sometimes that number is a fraction, like maybe 1/2, so you can also consider scale factors as numbers that you might be dividing by as well. So if you had a 1/2, that's the same thing as dividing by 2. All right, so is a dilation an isometry? It is not. It is not an isometry. So of the 4 that we're looking at, this is the transformation that is not an isometry, because an isometry needs to maintain congruency between the figures. And if you change the size, and that's literally all the dilation does, is it changes the size of it. So if you change the size of it, then it is no longer congruent. So this is not an isometry. For example number 1 for dilations, what we're going to do is graph a picture of a parallelogram, LM and P, and we're going to dilate that using point L as the center of dilation and using a scale factor of 2. Okay, so for every dilation, there's 2 things that need to be provided for you. One of them is going to be our scale factor, which scale factor of 2 for this one, and the other is the center of dilation. Now, depending on where the center of dilation is, it can really change the way that you're looking at the problem and you're thinking that it's done. However, there's going to be a general rule in how you're supposed to approach plotting all your points, which is to identify distances and then multiply those distances by the scale factor. So I want you to keep that in mind. This example is using one of the points as the center of dilation, but you could have the center of dilation at the origin. Those are actually the easiest of all the problems. Or you could have the center of dilation located inside of the figure, which again, it all looks a little bit different, but the way that you approach it by finding distances and then multiplying the distances by the scale factor is generally what the rule is here. Okay, so let's go ahead and see what this one looks like when it's all done. All right, so point L is going to be the center of dilation, and let's go ahead and figure out where M prime is going to be. We'll start with that, and I'll actually come back and talk about what we do with L at the end. Okay, so M, what we're going to do is think about how far M is from the center of dilation. So it's not so much about how far M is from L, but it's about how much M is from the center of dilation. L just is that center. Okay, so I would describe that as going over 1 and up 3. Okay, so I'm thinking horizontal and vertical components. It's over 1 and up 3. And what I'm going to do is I'm going to double that. Just going to double that distance. So over 1, up 3, get to M counts as 1. So I'm going to do it one more time. Go over 1 and up 3. And that is M prime. That's where that'll be located. Now N, to get to N from the center of dilation, the components would be 1, 2, 3, 4, 5, 6. 1, 2, 3. So it's a 6 by 3. So you're going to do 1 to get to N. You're going to do another 6 by 3 to make sure that we've got a scale factor 2. So 1, 2, 3, 4, 5, 6. Make sure I count that right. 1, 2, 3, 4, 5, 6. 1, 2, 3. So that's going to be N prime. All right, and then P, that one should be the easiest one because you just count 1, 2, 3, 4, 5, and then do another 5. 1, 2, 3, 4, 5. Nice straight line to connect them. And when I connect them, I should end up with a parallelogram that's just larger than the other one. So if it doesn't look like that, then maybe I'm off by a box, but hopefully I get it right. Yeah, it looks pretty good. I think I got it. All right, so that is your larger image that we got. Point L, because it is the center of dilation, that one doesn't end up in a new location. So L and L prime end up being the same. You can think it this way. How far is L from L? It's 0. And 0 times 2 is 0, so it stays in that spot. Now, if you had a different center, like say we use this point over here, which would be our origin. If you use the origin and still had a scale factor of 2, what we would do is look at L as being 1 by 2 away, and then you would have to double that, and L prime would be here. Then M would be 2 by 5, so you'd have to do 2 by 5 to get there. So wherever your center is, you're going to compare every single point to that one, how far away it is, what are its horizontal, vertical components, and then you double or triple or whatever you need, or maybe get a scale factor of 2.5. Right, whatever it is, you're going to change that pattern by, you're going to magnify that pattern by that amount. You can also have scale factors that are like 1/2. If you have 1/2, then you want to close in the space. So if we had a scale factor of 1/2 for this, then M prime would end up right here using the same center at L. But if the distance out to M is that, I would just cut it in half. So you can use all kinds of different scale factors. All right, neat observation about this. Our scale factor is 2. Is our new image twice the size of the other one? It is not. It's actually 4 times the size. It's actually 4 times the size. The part that has been doubled are all the side links. The perimeter is actually double. And if you were to add up all the links here, I know some of them are diagonal, but if you were to figure out all the links here around the edge, the perimeter of the larger one is twice that perimeter. You basically have 2 of these sides, you have 2 of these sides, you have 2 of those. So your perimeter is doubled, but your area is actually quadrupled. It's actually quadrupled.
Later, blah.